All right, guys, so we've got 2 lessons left, and we're not going to learn any more derivative rules. All the rules that we've done so far are rules that you'll be expected to know coming into next year. But we're going to be looking at some applications, and then we're going to look at a different type of way to differentiate on Monday. And those are going to be our last 2 lessons. So today we're going to do rates of change. So this is really from 2.2. But now that we've introduced some more derivative rules, we can apply it to functions that involve E or ln or compositions, products, quotients, things like that. So we're going to talk about motion, okay? And this is one of our big applications with derivatives, and when we eventually learn it, integrals as well. So we want to mention the rate of change, okay? So there's 2 different types of rates of change. There's average rate of change, and when you're talking about a function, that would be represented by the slope of the secant line. And remember, a secant line is a line that crosses a function in 2 points. And this function would be your position function, right? So if you have a position function and you found the slope of the secant line, that would represent the average rate of change, which would be total change in position divided by total change in time, okay? For example, if you travel 500 miles in 10 hours, your average rate of change would be 50 miles per hour because you do 500 divided by 10. But that doesn't mean that you were going 50 miles per hour at every single instant. So the instantaneous rate of change, okay, is what we call our velocity, and that would be the slope of the tangent line at a given value of x, or in this case, a given value of t, because t is the value that we're going to use for our independent variable. And more specifically, it would be the value of the derivative at that value of t. Okay, so remember, slope is always a value, so the derivative value, not the derivative function. Okay, so let's look at some application problems once we give our definitions and how we do our derivatives. So in terms of incorporating derivatives here, so if you're given x of t, which is an object's position, sometimes it's x of t, sometimes they might call it s of t, but they will tell you that it represents an object's position at time t. Then to find the velocity at time t, all you have to do is take the derivative of position. So this would be our notation, the first derivative, x prime of t. We could call that v of t. And t is the variable that we tend to use as our independent variable, not always, but most of the time when we're doing rates of change. And another thing that we could do is we could also find the acceleration. So the rate of change of velocity is acceleration. So if we took the derivative of velocity, that would give us our acceleration, which would mean that would also be the second derivative of position. Right? And those of you who have taken physics have probably thought about these concepts a lot, but you haven't really used calculus to determine them, and now we can. All right, so depending on what you're given, if you're given the position and you want to try to find velocity, you can take the derivative. If you are given velocity and you're trying to find acceleration, you're only going to take one derivative. If you're given position and you want to find acceleration, you have to take the second derivative. So let's look at a couple of examples. So here we have a diver jumps from a platform diving board that is 48 feet above the water. The position of the diver is given by this function. And this is a popular physics type function, but we're doing our problem in feet and seconds, not in meters. So it's a little different than something you might see. All right. But we've got our negative 16t squared plus 32t plus 48. This is a typical function when you're using acceleration due to gravity of any type of object, assuming that that object is in a vacuum. Okay, so this first question, part A, what is the diver's average rate of change on the interval from 1 to 2 seconds? So we want to take the change in position, all right, over the change in time. So here we're not doing any derivatives because this is asking for the average rate of change. So we're taking the position at 2 minus the position at 1 over 2 minus 1, which would be our change in time. So to find these 2 values, we just have to plug them into our original function. So if we plug 2 into our function here, we'll get 48. If we plug 1 into the function, we get 64. And we subtract that, we end up with negative 16, and feet per second would be our label for average rate of change. So that means from the interval from t equals 1 to t equals 2 seconds, the average velocity, all right, the average rate of change was negative 16 feet per second. If you're asked for speed, speed would just be the absolute value. All right, so the average speed would be 16 feet per second. All right. Okay, so let's look at part B. Okay, so same question, but what time does the diver change direction? So we need to think about how do we use this function to determine that. So for a diver to change direction, all right, so this diver is jumping up and then goes down. So we're not really going to use the position, but we're going to use the velocity. So velocity, since velocity can be positive or negative, we're really asking at what value of t does the velocity change sign? So change from positive to negative or negative to positive. In this case, since the diver is jumping up and then down, it will be when the velocity goes from positive to negative, all right? Because we're tracking the position from the water. Right? So when we jump up, the distance from the water is increasing, so the velocity would be positive. And as the diver jumps down, the velocity would be negative because the distance from the water is getting smaller. So in order for velocity to change sign, what would it have to equal? Well, to go from positive to negative or negative to positive, this would be a value where we equal 0. So really this is asking, when does the velocity equal 0? So we're going to find our velocity function, and that is by taking the derivative of this function, which is pretty easy. It's just a power rule. So you have to use any of your derivative rules necessary. And we get negative 32t plus 32. We're going to take this function and set it equal to 0. And then just solve. All right, so get t by itself, and we end up with t equals 1. And you can test it to make sure that the velocity does change sign here. If you plug in something like 1/2 into the velocity, you're going to get a positive value for velocity. If you plug something bigger than 1 in, let's say 2, you're going to get a negative velocity. So this is where it does change sign. All right, so after 1 second, that's where the diver goes from jumping up to now going down. Okay, so let's look at these last 3 parts. Same question though, same original function with position. When does the diver hit the water? Okay, so this is not when the velocity equals 0, okay, because the second the diver hits the water, the diver is not attaining a velocity of 0, there is a velocity there. This is asking, when is the position of the diver equal to 0? All right, so when does x of t, the position of the diver, equal 0? So we're going to just take our function here and set it equal to 0. Since it's quadratic, we want to factor. We can factor out a negative 16 from all 3 terms first to get t squared minus 2t minus 3, and then we can factor this quadratic, t minus 3, t plus 1, and we actually get 2 answers for t. We get t equals 3 and t equals negative 1, but keep in mind, this problem only exists on the domain t is greater than or equal to 0. We're not tracking the position of the diver before he jumps, so our only answer here is going to be t equals 3. Okay, so now for part D, find the diver's velocity at impact. Okay, so velocity at impact is not 0, even though right after something might hit the ground or hit the water, the velocity changes. But think about dropping a box from a window on the first floor and a window on the 20th floor. All right, the velocity at impact is definitely different for those 2 boxes. All right. So we're going to find the velocity, which we already found in the last part, negative 32t plus 32. And now, since we're trying to find the velocity when t is 3, because that's when the diver hits the water, we're going to plug 3 in for the velocity, and we get negative 64 feet per second. And the reason why it's negative is because at impact, the velocity, the position was getting smaller because we're getting closer and closer to the water. If it asks for the speed would just be 64 feet per second. All right, speed is just the absolute value of velocity. And then for part E, find the acceleration of the diver when he hits the water. So our acceleration function, which would be the derivative of velocity, is actually a constant. So it doesn't matter what t is, acceleration is always going to be negative 32 feet per second squared. And if you are a physics person, and remember this is actually a constant acceleration due to gravity. All right, negative 32 feet per second squared. If you were doing this in meters, you would have gotten negative 9.8 meters per second squared. All right. And the reason why it's per second squared is because you're finding the rate of change of velocity. So feet per second would be rewritten feet per second squared. All right, so let's look at one more example, and this one has a trig with some chain rule. So a particle moves along a line. Okay, so now we're not doing up or down, we're moving along a line, so particles moving left and right. And again, these are called rectilinear motion problems. Okay, later in calculus, we'll do parametric motion, but for now, we're just tracking one position. That last problem, the diver, we were just tracking the height of the diver over time. Here, we're just tracking the x coordinate of a particle that's moving along a line. So picture this line, and we have a particle here, and it keeps moving along the line. All right, so it's not moving up or down, it's only moving in this position. Okay, so for part A, find the velocity at time t. So this is position. So to find velocity, we just have to take the derivative. Derivative of 2 pi t. Okay, that's just your power rule. That's just your coefficient. So that's just going to stay 2 pi. Derivative of cosine of 2 pi t. We've got to use our chain rule. So we take the derivative of cosine first, which is negative sine. Keep what's inside, and then multiply by the derivative of the inside, which is just 2 pi. So that should give us this. So 2 pi is the derivative of the first term. Then minus sine, keep what's inside, and then we multiply by the derivative of the inside. All right. So here's our velocity function, and that's as simplified as it can get. You can factor out a 2 pi if you want, but we can leave it like this as well. Next, find the acceleration at time t. So again, the acceleration function at time t would be the derivative of velocity. So the derivative of 2 pi, which is just a constant, will be 0. Negative 2 pi is a coefficient, so we're just going to keep it out in front and then take the derivative of sine of 2 pi t. Derivative of sine is cosine. Keep what's inside. Derivative of the inside is 2 pi. So we've got our negative 2 pi, that stayed, and then we've got our 2 pi cosine 2 pi t. And then we can just multiply our coefficients together. So negative 2 times 2 is negative 4. Pi times pi, we're just going to write as pi squared, and then cosine of 2 pi t. And then for part C, what are all values of t going from just 0 to 3, for which the particle is at rest? So at rest means velocity has to equal 0. All right. So we're going to take our velocity function, and we're going to set it equal to 0. And now we have to solve this. So this one's a little trickier because now this is a trig equation we're trying to solve, but this is something we did this year. We did it in chapter 5, solving trig equations. This is why it's imperative you keep your notebook from pre-calc, because there are going to be a lot of things that we're going to refer back to when we're doing some of the algebra in calculus. So to find the zeros here, I'm going to subtract the 2 pi over. All right, we get negative 2 pi on this side, and then we can divide both sides by negative 2 pi, which will give us this. And now we need to solve this equation. So before we deal with this 2 pi t inside, we're not allowed to divide it over because it's inside. What we're going to do is just think about this as theta. All right, we're going to do a substitution and figure out, well, when does sine of theta equal 1? All right. So sine of theta equals 1 using your unit circle. That's at the top of your unit circle when your y coordinate is 1. That happens at pi over 2. And then if you keep adding 2 pi, you can get the coterminal angles, 5 pi over 2, 9 pi over 2, 13 pi over 2, and so on and so on. We don't have to list them out because we're only going to solve for values of t that are between 0 and 3, which is why I didn't put any negative angles here. So now what we're going to do is, since we replaced 2 pi t with theta, now we're going to go back and replace our theta with the 2 pi t that we had here and solve for t. Because our goal is not to solve for theta, our goal is to solve for t. So when does 2 pi t equal any of these values? To get t by itself, we just have to divide by 2 pi, or we could say multiply everything through by 1 over 2 pi. And the pi's will cancel. So here, when we divide this term by 2 pi, or multiply by 1 over 2 pi, the pi's will cancel and we'll get 1 over 4. Same thing here. The pi's will cancel. We'll get 5 over 4. Here, the pi's will cancel. We'll get 9 over 4. Then we'll get 13 pi over 4. But the second we hit 13 pi over 4, we've now gone over a value of 3. So the only 3 answers that would be in our domain here from 0 to 3 would be t is 1/4, t is 5/4, and t is 9/4. Okay, so you could be given any position function that involves any functions that we know how to take the derivative of using power rule, product rule, quotient rule, trig derivatives, ln, chain rule, all right, anything like that, now that we know our application. Okay, so the worksheet that's going to be not very long, it's actually going to be due on Monday, and we're going to do our last lesson on Monday with implicit differentiation. Okay, so keep that in mind. If you have any late assignments from chapter 12 or on, you can still hand those in for credit. All right, and I will see you guys back here on Monday. Have a good weekend.